Hi guys, it's Kate. This is problem 4 from the worksheet in class that was the final day on exponential functions. And what's interesting about this is it doesn't do very much that's particularly new, but it combines a lot of different skills that we've done over the course and is really worth a closer look. So let's get started. We have this function, 3x over e to the x, and it's an example of a surge function. And the problem gives us a little context. It says this type of function is used to model lots of different types of situations. And an example that's given is the amount of an intravenous drug in the blood X minutes after the drug is administered. And apparently that can be modeled as a surge function. So the idea behind this entire problem, as you glance over how it's going to flow, is that we're going to look at the derivative. We're going to take a look at when the derivative is positive and negative. We're going to try to determine when the function is concave up, and then we're going to see what the various limits are, and then we're going to synthesize all of this information and we're going to try to draw a picture of the function. And these types of problems can be very challenging for students. Not that the individual pieces A, B, C, D, and E are challenging, but the ability to keep all that information in your head and then synthesize a picture out of it. So we're going to go through this and give it a whirl, and I'm going to talk about tips and tricks that you can use in problems like this one. So let's get started. The very first task at hand is for us to compute the first derivative of this function, f prime of x. Now, you guys have lots of experience with this. You've done it on the problem set already. One quick and easy way is to express this as a product, saying that instead of calling it 3x over e to the x, we call it 3x times e to the negative x. Let's do that and then apply the product rule. Take a couple seconds, try it on your own. In the next few seconds, the solution will appear here. All right, here I've just used the product rule and I ended up with 3 times e to the negative x plus 3x times negative e to the negative x. And I just algebraically rewrote that, made it a little bit cleaner. That yellow underlined portion is the result that comes out the other side. 3 times e to the negative x minus 3x e to the negative x. Now part B asks a follow-up question, which says for what values of x is f prime of x positive? For what values of x is f prime of x negative? And right away it should be pretty clear to you that this format of our solution from part A is not super useful to very quickly being able to reason about the sign of the derivative for various values of x. And so what we need to do is we need to algebraically rewrite that derivative so that that becomes more apparent. And the quickest way to do that is to factor out anything that these terms have in common. So for us, that's both the factor 3 and the factor e to the negative x. Those appear in both cases. Let's take a look at what happens when we do that. So I've gone ahead and done that. Now it's even more useful and you'll develop a better and better intuition for this type of algebra, but it's even more useful to fully rewrite this as a fraction instead of expressing it as a product with e to the negative x. So this has now become 3 times 1 minus x all over e to the x. So this is the format where it is much easier to determine for what values of x this expression, this derivative, is positive, and for what values of x it's negative. Remember that this is exactly what we computed in part A. It's just rewritten in order to answer this question in a much more straightforward manner. All right, so let's take a look at this. For what values of x is f prime of x positive? What values of it is it negative? It's important to look at both the numerator and denominator in reasoning about this. Now, when we look at the denominator, we see e to the x is down there by itself, and e to the x is always greater than 0. It's just impossible for it to be negative. So if there's any way for this derivative to change sign, it's going to depend entirely upon the numerator. So if the numerator is positive, you're going to have a positive number over a positive denominator, and that's going to be overall a positive value for f prime. If the numerator is negative, you're going to have a negative numerator over a positive denominator, and that's going to be a negative number for f prime. So everything depends on the numerator to determine the sign. So all of a sudden, all we're really looking at is 3 times 1 minus x. and asking ourselves, hey, when is that positive? When is that negative? Well, to simplify that even more, 3, right, is always positive. So really the sign change is coming from the 1 minus x chunk. If the 1 minus x chunk is positive, the whole thing will be positive. If the 1 minus x chunk is negative, then the whole thing will be negative. And with that simplification in mind, we can now answer this in a pretty straightforward manner. If x is less than 1, that 1 minus x term will be positive. 3 times that will be positive, and 3 times that over e to the x will also be positive. So if x is less than 1, the numerator will be positive and the whole fraction will be positive because the denominator is always positive no matter what x is equal to. Now, alternatively, right, if this little piece right here is negative, then it's going to make the entire numerator negative. And since the denominator is always positive, it will make the whole derivative negative. So that means that if x is greater than 1, the numerator will become negative. And so f prime itself is going to be negative as well. Now already this is significant. Since we skimmed the problem at the top of the question, we know that the whole point is to sketch the graph of f at the end. And so even though it's just asking me, hey, when's the derivative positive? Hey, when's the derivative negative? What I really know is that what that means for the graph is, hey, when the derivative is positive, the function's going to be increasing. When the derivative is negative, the function is going to be decreasing. And so I make a note over in this left-hand margin to myself. I say, hey, self, if x is less than 1, the derivative is positive, which means the function is increasing. And if x is greater than 1, the derivative will be negative, which means that the function is decreasing. And so in green over here, I've written this is an important takeaway. When x is less than 1, the function's increasing. When x is greater than 1, the function's decreasing. All right, our next question is, for what values of x is the function concave up? We know a few things about that, and vice versa for concave down as well. It says give exact answers. And for us, we know that when the first derivative is increasing, when the first derivative is increasing, the function can look like this. It is either decreasing at a decreasing rate on this side or increasing at an increasing rate. Regardless, first derivative increasing means that it is concave up. First derivative decreasing, well, it looks like this shape. It means that either it's increasing at a decreasing rate or it is decreasing at an increasing rate. Either way, it means that it's concave down. And of course, note that when the first derivative was positive, that meant that the function was increasing. When the first derivative was negative, that meant that the function was decreasing. So if the first derivative is increasing, that means that the second derivative is positive. When the first derivative is decreasing, that means that the second derivative is negative. And so if the question is asking us, where is the function concave up, where is it concave down, it's really asking us, where is the second derivative positive, where is the second derivative negative? And so we can assemble a plan. We're going to calculate the second derivative, probably going to have to re-express it again in a way that makes sense algebraically for us to look at it very quickly and know where is it positive, where is it negative, and do the same analysis we did in part B with the first derivative, only with the second derivative. Let's do it. I'm going to use part A's expression of the first derivative up here to employ the product rule on some of these terms, and the sum rule, I guess we called it overall. So let's compute. Let's take this. This is our first derivative. We're going to take the derivative of that to get the second derivative. All right, so here that is. You have to be pretty careful at a couple of points that I'd like to call out. One is how you're going to deal with this negative sign right here. I elected to sort of leave it out front and then put parentheses entirely around the product rule derivative that came out of this. But then you have to make sure that not only do you manage the negative factor in here, but you're also distributing the negative factor to both of these terms. So I ended up with negative 3e to the negative x minus 3e to the negative x plus 3x e to the negative x. And these two terms will combine into negative 6e to the negative x plus 3x e to the negative x. Now, similar to how we went from this expression of the first derivative to this expression of the first derivative, I noticed that both 3 and e to the negative x are common factors in both of these terms, and I factored them out. Now I've expressed it as a fraction down here in the denominator and factored out the 3, and now all of a sudden I'm looking at just x minus 2 as the factor that's controlling the sign of this second derivative. And so similar to how we answered b, what we found here is that, hey, if x minus 2 is positive, this whole thing will be positive. If x minus 2 is negative, this whole thing will be negative. So for us, in order for this to be positive, x needs to be greater than 2. In order for it to be negative, x is less than 2. So synthesizing that, we have that if x is greater than 2, the first derivative will be positive, the second derivative will be positive, and therefore the function will be concave up. If x is less than 2, the second derivative will be negative, and the function will be concave down. I'm going to rewrite that as in our important takeaways column over here, because that's a piece of how we're going to need to sketch this function. All right, moving right along, we're now asked what's the limit as x approaches negative infinity for just the function f? What's its limit behavior as x decreases without bound? All right, let's rewrite the function down here nice and fresh. So what this question is really asking is, if we're asking about the limit of f as x goes to negative infinity, we're asking about the limit of 3x over e to the x as x goes to negative infinity. That means that the denominator, as x decreases without bound, we know that this function's limit behavior right here, as x decreases without bound, we know that this goes to 0. This approaches 0 when you raise e to a larger and larger magnitude, but negative power. However, the numerator, 3 times x, that decreases without bound as x goes to negative infinity. So this also goes to negative infinity. And if you're taking something really large negative number and you're dividing it by some really small positive number, then your ultimate result is that this whole thing is going to just become a very large negative number that's increasing, increasing, increasing without bound. So this whole limit is also going to be negative infinity as a result. You're taking something very large and negative, large magnitude, negative sign, and dividing it by small magnitude positive sign, right? The numerator's limit is negative infinity, the denominator's limit is 0 from the positive side. And so your net result is that this limit is going to equal negative infinity. Our next piece now is finding the limit as x approaches positive infinity. We're going to go through the same reasoning. Let's write down the limit we're taking. Now the question is, what happens to both the numerator and denominator? Well, the numerator, as x grows without bound, is also going to grow without bound, and the denominator grows without bound as well. They're both going to positive infinity. Now the question becomes, which one goes faster? Well, which one grows faster, a linear function, 3x, or an exponential function, e to the x? We know that the exponential function grows much faster than a linear function, right? It's a constant percent growth as opposed to a constant amount growth. So this is going to increase much, much faster. It's eventually going to outpace and never stop outpacing the 3x for any particular value of x. As you increase x, the difference between e to the x and 3x just keeps increasing and increasing and increasing. You can imagine this by looking at some sort of sketch in your head that looks like this. There may be moments right at the start here where the exponential function might be lagging behind. The linear function can catch up for a second, but eventually as the exponential function really starts to increase, this linear function just will not be able to catch up, and as it continues to increase, it really just leaves this linear function behind in the dust. And so even though both the numerator and denominator are going to positive infinity, meaning they're growing without bound, The denominator increases much faster and continues to increase more and more quickly compared to the linear function, which means that, wow, that denominator is getting much, much bigger than the numerator, and that difference will only grow without bound. So that means the whole fraction, 3x over e to the x, when a denominator grows much faster than a numerator and continues to do so, this thing is going to go to 0. All right, so we have our 3 pieces of information. We have sort of where it's increasing and decreasing. We have where it's concave up and concave down. And we know what its limit behavior is on either side. And so now we need to put all those things together to sketch a graph of f. You don't want to do this all in one go. Start with your axes and what the relevant points are to show on your axes. And since we know that it goes from increasing to decreasing at x equals 1 and concave up to concave down at x equals 2, that's where we want to make sure we show on our graph. I'm going to put in some notes for myself that come from our work in parts B and C, as well as D and E. But for instance, I want to say to myself, hey, everything to the right of 1 is going to be decreasing, to the left of 1 is going to be increasing, based on what we got from part B. Similarly, we know it's concave down for x less than 2, and then concave up for x greater than 2. That's from our work in part C. I'm going to put those notes in as well. So already from the increasing and decreasing point, we know that at 1, there's probably a max, right? If it's increasing, increasing, increasing through here, and then it's decreasing, 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 we know there's going to be a little hill here, and we want to know how tall is that hill. Well, I need to figure out what the function value is right at x equals 1, so I'm going to do a little scratch work on the side. And if we think about what we know about the size of e, which is about 2.7 and change, this is going to be something that's a little bit greater than 1, but not by much. I am going to label that point, though. It's important. I'd also like to know where there's an intercept. When is this equal to 0? Well, looking back at the original function, I know that there's no way for the denominator to equal 0, so there are no asymptotes, right? The numerator is controlling when this function is equal to 0, and that happens right at x equals 0, so I'm going to put that point in. And then last but not least, I'm going to remind myself that as I move towards negative infinity, this function needs to be decreasing without bound. So I'm like, when I move over here, I'm moving down to negative infinity. And then when I move to positive infinity, right, this should be approaching 0. So we're going towards 0 over here. That's from our work in D and E. Now we're going to give it a whirl. We need to move through these 2 points. Let's give it a whirl. All right, moving through these 2 points right here and also increasing but being concave down, I'm going to try and trace that out. Here we go. Concave down, moving through these 2 points. Excellent. Now it's still going to be concave down, but it's decreasing now. And then as it hits 2, it turns into concave up. We're moving towards 0 in this limit, and we're done. It does all the things that we deduced in our parts of the problem. It needs to be increasing until 1 and then decreasing thereafter. It needs to be concave down until 2 and then concave up thereafter. It needs to be going towards negative infinity as we decrease x without bound. It needs to be going towards 0 as x increases without bound. It's doing all those things, and we even got a little bit of additional help of where is that 0. We found that out by observing the function f. Where is that small max there? We did that by evaluating at a particular point. And there you go. A sketch. We're done. If you have any questions, please don't hesitate to ask. This problem and many more like it will appear again and again as we get more and more experience with different functions and their derivatives.